Behind the scenes. Conversations with European researchers and innovators.
If you had giant radio eyes that were sensitive enough to see radio waves over the whole sky, it would be like fireworks. You would basically see one fast radio burst popping off somewhere on the sky every 10 seconds or so.
In this podcast, we'll hear the inspiring stories and journeys of Europe's most brilliant scientists and innovators whose discoveries are having an impact on our daily lives. Here's how they got to where they are. These are our top stories. Our guest today is Jason Hessels. He's talking to us from the Netherlands, where he is a radio astronomer and professor at the University of Amsterdam. He's currently working on Dragonite, an EU-funded project which is tracking down the host galaxies of fast radio bursts. Jason, thank you very much for joining us.
Hi, thanks for talking with me.
Before talking about your project, tell us more about yourself and your chosen field. How did you get into it?
Astronomy became a passion for me when I was a teenager. At first, I was thinking about perhaps going into medicine, perhaps becoming a surgeon. But I think it was, the movie Contact that came out when I was a teenager, in which radio telescopes feature very prominently, in which Jodie Foster is a radio astronomer looking for signals from aliens using very large radio telescopes. It really captured my imagination, the scale of these huge instruments and what was possible with them. And I got very quickly hooked and decided to go into astronomy instead of medicine.
And was it the tech side, the cool tools that you got to use, or were you lying in a field stargazing with your eyes as well?
Part of it was certainly the scale of the instruments. Part of it was also the scale of the things that one would be studying, studying the whole universe, things that are very, very far away, very mysterious. And I also kind of came to the realization that maybe I was more interested in answering fundamental questions than I was in practicing the specific area. I realized that maybe I was more interested in trying to push the boundaries of knowledge than to practice a certain technique at a very high level of expertise.
Is that what you expected when you set out on this career path? How did you get into it? How did you pursue it? And how did you find a goal to attach your direction to?
I was very inspired by the scale of the problem and the scale of the instruments that were involved. I think I was also really inspired by the fact that it's so fundamental, that a lot of the stuff that we do is really fundamental in the sense that we're trying to understand the nature of gravity by studying these extreme stars. We're trying to understand the extreme of matter, which is relevant for understanding what is particle physics like in extreme situations. And in terms of, selecting a particular direction within an astronomy, I think, I immediately gravitated to the type of things that could be studied with radio telescopes, these giant instruments, because that's what captured my imagination as a teenager. And I was really fortunate, actually, that when I started my PhD in Montreal back in 2001, it was possible, as part of my PhD project, to actually use the same telescope, the Arecibo telescope that features in the movie Contact. And, from that point on, especially since it connected so directly to what inspired me in the first place to start studying physics at university, I've never left that area because I find it's an incredibly rich and fulfilling area of astronomy to work in.
That must have been quite a life goal, a life-changing moment to get to you. Is that the very thing that inspired you in the movies?
Exactly. My jaw dropped when my new supervisor, a PhD supervisor, said, well, I need you to go to Puerto Rico this summer and use the Arecibo telescope. And I thought, how can this be possible? This is exactly why I went into astronomy in the first place.
So are you still like Jodie Foster, looking for aliens that you want to discover something new and exciting?
Not at all, no. My research does not focus around aliens. It focuses around primarily neutron stars, which are pretty phenomenal objects. These are stars that have collapsed at the end of their lives when they've run out of fuel and they can't shine anymore. Some of these sources, we know them as radio pulsars. These are stars that send out radio light, and as they rotate around, almost like a cosmic lighthouse, we can see flashes from these neutron stars. And in more recent years, I've started studying a very enigmatic phenomenon, these fast radio bursts, which are flashes of radio light, which in some ways look similar to the flashes that we see from these pulsars, but we now know that they come from billions of light years away and hence must come from something that's much more energetic, that can produce a lot more energy and produce hence something that's still visible even though it's very, very, very far away. And what motivates me quite a bit is to really try and understand, because it's part of what makes us human to, have that curiosity about why are things the way they are, and also have that curiosity, where do we come from? And this aims in the most broadest of senses to answer that question in the most fundamental of ways possible.
What do you think might be the practical sorts of outcomes from the work you're studying?
So I think a lot of the applications of the fast radio burst phenomena are related to studying astrophysics and cosmology. These radio flashes are coming from very, very far away, billions and billions of light years. And, in the same way that you could imagine someone shining a flashlight on the other side of a football pitch or something on, say, a foggy day, you can imagine that light illuminating, all of the water in the air and maybe the dust in the air. And you can see all of the things that you wouldn't see if someone wasn't flashing that flashlight towards you. In a similar sense, we're incredibly fortunate that nature has given us this incredible tool, these flashes of radio light coming from billions of light years away, which are also kind of illuminating all of the material between us and that source, between galaxies, between stars, and allowing us to kind of study the distribution of matter in the universe, which is really fundamental for understanding why is the universe put together the way it's put together. Why do galaxies have the sizes that they have? What's between galaxies? How can stars grow as a function of time? And all of these things contribute to an even more important question, which is very close to home. Where do we come from? Why do we exist in the first place? Because to have human beings, you need a planet. To have a planet that can support life, you need a star. To have a star, you need a galaxy. To have a galaxy, you probably need a cluster of galaxies. And you can trace this all the way back to the Big Bang that started the whole show.
How do you do that? How do you go about collecting it? And what do you use?
So one of the main tools that we use is the LOFAR telescope. And LOFAR is basically a collection of antennas, like not so unlike, say, the antenna on the hood of a car, which can receive, in the case of a car, radio waves coming from a radio station. We have thousands and thousands of these, and they're spread across the Netherlands. They're spread across Europe as well. And what you need to imagine is basically, these radio waves coming from deep in outer space. They're coming towards the Earth, and they're coming into the Earth's atmosphere. And each one of those antennas can measure how strong those radio waves are. And by comparing the signals between these thousands and thousands of antennas, we can figure out where the radio waves are coming from. And we also need to collect the signals of many individual sensors, if you will, because otherwise the signal would be too weak to be able to detect. But then we have thousands and thousands of measurements that we're all bringing together. The amount of data that's streaming into the central supercomputer of this telescope, like, 200 high quality movies per second streaming into this computer, and you need to be able to do something with it in real time. So one of the other aspects of radio astronomy that I find really fascinating is there's really strong connection to high performance computing and to data science, because just like particle physics, which is another great example, we're pushing the extremes of big data and high performance computing to be able to make the next step in the scientific questions that we want to answer about what's in deep outer space.
Is a lot of it programmed or machine learned?
That's becoming more and more important, actually. And unfortunately, one of the reasons why that's becoming more and more important is not just because the amount of data is large, but it's because the amount of interfering signals is becoming larger and larger. So there are a lot of things that produce radio waves that are human made as well. And it's almost like, trying to study something that's very faint while someone's shining a flashlight in your eye. It's hard to see when someone's shining a flashlight in your eye. We have to use machine learning techniques to separate the signals that we find scientifically interesting from this huge sea of other signals that are being produced.
Okay, well, I understand you've recently become a professor yourself, so you're passing on all this enthusiasm and interest to new students. How are you doing that? And how is that going during COVID-19?
Yeah, COVID has obviously had a huge impact on what we're able to do. I would say in some ways, though, it's been positive, and maybe I should focus mostly on the positives of it. I mean, we're all working from home, and we're connecting using Zoom and Slack and all of these other tools that fortunately exist now. It's a very different world than, for instance, when Isaac Newton was, at home developing some of his theories because of the pandemic that was going on in Cambridge during his day. So fortunately, we can connect to each other with modern technology. And one of the positive things about that is that it's really enabled new ways of working. I have a postdoc, for instance, in my group who is continuing just to work from Sweden because that's where his family is. And it's almost seamless. I mean, we have group meetings, and there were people spanning Europe that are part of a single research group, all talking to each other fluidly, all getting along, chatting and joking and whatnot, because it's possible with video conferencing to do this. And this wouldn't have been possible 10 or 20 years ago. And for my research, that's particularly important because, again, the instruments that we use are also geographically distributed.
So what has been your experience of multi-country EU projects and programs?
Very positive. The instruments that I use are primarily the LOFAR telescope, which, as I said before, these are antennas that span many European countries, and we're in the process of trying to make the LOFAR telescope a European Research Infrastructure Consortium, a so-called ERIC. And for the science, it is absolutely critical to have a pan-European approach. And the other instrument that I'm using very much for my research right now is the European VLBI network. And it's in many ways a similar telescope to the LOFAR telescope, just operating at shorter radio wavelengths, so higher radio frequencies. And that as well to achieve the precision that we want to pinpoint these sources on the sky, and to also study the signals with the highest possible time and frequency resolution, to chop up the signals in all the ways that are scientifically interesting. We need instruments that span the European continent. And the European VLBI network is also one of these European research infrastructure consortiums. And so my experience so far has been really quite positive. I come from Canada originally, but I've been impressed with the level with which European countries can work together to construct these mega instruments that are necessary to do cutting edge science.
What would be your advice to your younger self or to new researchers?
I wish that someone would have told me at an earlier stage to not focus on problem sets and exams and getting good grades. I mean, that's important to a certain level, right? Because one needs to progress, through the system that exists. But I wish someone would have sat down with me as a young student and said, focus on understanding things more deeply, focus on learning how to figure out things on your own and to learn on your own. Because if you want to become a researcher, research is not about a bunch of questions that we know the answers to and answering questions where we don't know what the answer is, and even more fundamentally, coming up with questions that we never thought to even ask before. And that takes a much higher level of understanding. You need to synthesize many things together. You need to be very creative. I think it's been my experience that I've had a number of students who, some chagrin say, I didn't get very good grades at university, but I would really like to work in this research area. And you kind of look at what practical experience they have, and they start off and you see what they're able to do. And in some cases, there are students who do very poorly in the standard university setting who end up being fantastic researchers because they just have that ability to roll up their sleeves and figure things out and make things happen. Yeah, it's a different skill to sharpen compared to learning how to apply theory and answer problem sets and write exams.
And then how will the history books record Jason Hessels and the work you're doing? Do you think about some sort of game-changing moment?
I'm not sure about myself specifically, and I don't dare to I don't dare to speculate. But I think the area of study that I'm working in right now, this fast radio burst phenomenon, in the last 10 years that I've been working in this field, I've only seen kind of the richness of the scientific questions and the applications. So I think this is an area of astronomical research that is going to be around for half a century still, and might become transformational at some point. It might lead to an insight that is really quite shocking.
Well, now on to the details. We asked Polona, our previous guest. She's a researcher working on snow and ice models based on data collected as part of the Mosaic Arctic expedition. Really fascinating work, but we asked her to put a question to you. So here it is. We've been working and talking about improving climate models. I imagine Jason and his team use some numerical models. So what improvements would their models need?
What improvements do we need to our numerical models? I think one of the biggest limitations that we still have is this issue of separating the astronomical signals from human-made signals. And it's really like a needle in the haystack type of problem, which has been aided in many ways by machine learning techniques. But what I find a bit dissatisfying about applying machine learning technique to this type of problem is that in practice, it appears to work quite well. But what is potentially concerning is at some level, one loses grasp on what these algorithms are actually doing, and hence what is being found and what is not being found. And are we not finding the things that we had no idea existed? Are these algorithms creative enough to find the things that we don't expect? And that's, of course, where much of the very interesting science is. And I think in terms of improving our numerical models, I want to think of more creative ways to search through the data.
And our next guest in this series will be Alicia Perez, CEO and co-founder of Libelium. That's a Spanish IT company that's created WASP Mode, which is a wireless modeler and open source center hardware platform for the Internet of Things. Is there anything you would like to ask her?
I was looking through the website. I thought it was really interesting in the sense that the instruments that I use are also remote sensors. Basically, we have over a large geographic area. I was wondering whether that sensor network could also be used to kind of measure the level of electromagnetic interference, the level of non-visible electromagnetic waves at various geographic locations to help us, for instance, get better measurements of electromagnetic radiation from space.
Thank you so much for talking with us today, Jason. More information on your project can be found online. Check the details of the episodes for all the links and more information. Thank you for joining us today. And remember, even if your grades may not be up to the best, you can still be good researchers, so don't give up on your dreams. This podcast series is brought to you by the European Commission, and you can find it on all listening platforms. If you enjoyed this conversation, rate this podcast on all listening platforms and share it with your friends on social media.